Hello together, I'm Aaron Schneider. I'm a master student with Bertram Bitsch at the MPIA in Heidelberg. And today I want to talk about my master thesis project, the chemical composition of planetary atmospheres due to accretion. Here in this beautiful image, you can see a protoplanetary disk and a protoplanet. And my question is, what is the atmospheric content and the content of the planet in heavy elements and in C/O? So to do this, let me talk about some observational constraints. Today we can observe different exoplanets, and this is a plot of by Forngreen of the heavy element mass from interior models. So basically you measure the mass and the radius, and then you can infer how many heavy elements do you need to put into the atmosphere and the core in order to get such a radius. So this is one observation. A different thing that you can observe is the C/O ratio of the atmosphere. This is a plot by Brewer et al., who compared the C/O ratio of a planet compared to the host C/O ratio. So in my master thesis, I now want to look at the planet formation path and how this can influence the observational constraints. So to give a short overview of planet formation, we can nowadays observe micrometer to meters to centimeter size objects like dust and pebbles in protoplanetary disks. We can also observe asteroids in our solar system, and we can also observe trans-Neptunian objects. We can also observe exoplanets, but we don't know what's in between. So this is the question of planet formation. So the question of planet formation begins in a disk, and I want to talk about my disk model at the beginning. So in order to model the disk, I will try to include as much as possible. First of all, we need gas and dust evolution. We also include viscous heating and stellar irradiation. We try to form the planetesimals, and we also need chemical compositions in order to infer the planetary composition later on. And we include evaporation at the ice lines. And some important parameters, of course, I want to show you are the dust to gas ratio, which we set to 2%, the fragmentation velocity, which we set to 5 meters per second, and the planetesimal forming efficiency, which we set to 1%. So now let me show you some graphs of my disks. This is the surface density profile for pebbles in blue, planetesimals in red, and gas in black. And we now see the evolving disk for a static case, which means we have no evaporation. So in case of no evaporation, we will see that the pebbles drift inwards and get converted to planetesimals. And of course, the gas also moves a bit. So this was a disk with alpha 5 times 10 to the power of -4, a disk mass of 0.128 solar masses, and a cutoff radius of 137 AU. If we now have a disk with evaporation turned on, which means that we convert pebbles that drift over the ice line into gas, we will also convert gas which drifts over the ice line in the opposite direction by condensation into pebbles, which means that we have an enormous pile up at the ice lines, which we will see here. And we also have this pile up because of the planetesimal formation by pebbles in the planetesimals. So this is what you can see here. You see the pile ups, and you can see the pile up also in the planetesimal surface density. So how about the C/O ratio? In the static case, which we see here, the C/O ratio will only change marginally due to the cooling of the disk, which you see here. But in case of a disk with evaporation turned on, we have much more enrichment in C/O beyond the CH4 ice line, because we evaporate C and get C into the C/O ratio. We will have an enrichment in O because we evaporate H2O. This is what you will see here. You will have a decrease in C/O beyond the water ice line. So if I run this movie, you will see the C/O content goes down here and increases beyond the methane ice line. So what does this mean for our planets? For planet formation, first of all, we need to migrate a planet. So a planet migrates through the disk by type 1 migration if it's a low mass planet, migrates by type 2 migration if it's a high mass planet, and then there are also feedback processes, which we include by dynamical torques and heating torque, which includes the accretion luminosity by pebble accretion. Then to grow the planet, we use pebble accretion, planetesimal accretion, and gas accretion in the rapid accretion phase and in the contraction phase. Before we reach the pebble isolation mass, we will accrete 90% of the material into the core and 10% into the atmosphere. When we reach pebble isolation mass, which basically stops the solid accretion, we accrete nothing into the core, but everything into the atmosphere. So in case of parameters, we use planets that start at 100,000 years with a steering parameter of 10 to the power of -4, which basically sets the inclination of the planetesimal population. We use planetesimals with a radius of 50 kilometers and an envelope opacity of 0.01 centimeters squared per gram. So I now want to show you some growth tracks. These are basically the radius where the planet is located, and here you have the mass. And if I start with a free AU starting planet, it will get a hot Jupiter, and you don't really see a difference between planets that have evaporation turned on in the disk and disk without evaporation, which is the dashed line. If I now show you a warm Jupiter, you will also see a planet that migrates a bit outwards due to the heating torque and then slowly migrate inwards. And the same for a cold Jupiter. But how about the C/O ratios? I now want to show you the C/O ratio in the atmosphere of the planet. And the C/O ratio for the hot Jupiter is quite different from the C/O ratio without evaporation. For the warm Jupiter, we also see this effect of the methane and the water ice line. And for the hot Jupiter, we also see this effect. So now you can see the cold Jupiter, the warm Jupiter, and the hot Jupiter have very different C/O ratios at the final position. While the evaporation turned off, these planets don't really make a difference in C/O ratio and are quite the same. So we propose that we will only see this change when we turn evaporation on. So how about the heavy element content? The heavy element content, we try to reproduce this figure by Thorngreen et al. By varying the alpha parameter, the dust to gas ratio, the disk lifetime, the starting position, and the starting time. And we put all of this together into a parameter mesh and then try to reproduce this plot. So now with the color coding of alpha, you will see our own version of the Thorngreen plot, with the hot Jupiter planets being bullets and the cold Jupiter planets being crosses. Those are probably not observed in the Thorngreen plot. However, you can see for low alpha, there are only planets with few Jupiter masses. And for higher alpha, we get more and more massive planets. This because of the mass accretion rate, which is proportional to the viscosity. Now, how about the dust to gas ratio? The dust to gas ratio basically sets how many solids we can accrete. And solids, of course, contribute to heavy element mass quite high. So if we have a low dust to gas ratio, we get planets with low heavy element mass. If we have higher dust to gas ratio, we might even reproduce the Thorngreen fit. So in this case, with 3% dust to gas ratio, we get a very similar fit like Thorngreen. Now I want to show you the same planets in a different manner. This is a ternary plot, which says that if you have a planet located here, you have 100% of heavy elements coming from the pebbles. Here you have 100% of the heavy elements coming from planetesimals, and here you have 100% of the heavy elements coming from the gas. So what you can see here, for example, for this planet, is that this planet is made up 17% by pebbles in the heavy element content. It is made up 35% in gas of the heavy elements, and it was made up by 48% in the planetesimals by its heavy element content. So what can we learn from this graph? We can see that planets that are very massive are more likely to be made up by gas and by pebbles. The heavy element content don't really come from planetesimals. So to sum up and conclude, I want to say that we did viscous evolution of disks and included evaporation. We put a planet into this disk and accreted with pebbles and planetesimals and gas. And then we looked at the heavy element content and the C/O ratios and compared it to observations. We can conclude that planetesimals try to explain the heavy element content, but in our models, at least, they fail with it. And we can also conclude that the evaporation is quite efficient in order to enrich the gas and heavy elements. And with this, I want to thank you for your attention.